Thank you everybody for joining. I'm Faith Westort from Elastic's community team. So if you're coming from our Amera virtual user group, hello, and welcome to the Cincinnati user group. Clint Wolff, who is a lead search engineer at LexisNexis, is leading today's presentation, and he's also one of the community organizers for the Cincinnati group. So we're really lucky to have him both as an organizer and as a speaker today on how Elastic powers Nexis Diligence. So this presentation will be recorded and it'll be potentially available to you at a later date. Not sure about that. Gonna send you some quick links to our user groups so that you can join them if you're not already a part of it. Without further ado, I'm gonna hand things off to Clint.
Alrighty, thank you very much, Faith. I think Faith kind of covered my intro for me. So I do want to just second her welcoming of everybody, especially the Cincinnati user group folks. Hopefully we'll be able to see all you guys in person here as soon as things get back a little more normal in the world. And of course, one of the great things is, for doing these in a virtual fashion is that we're able to have folks from other user groups join us as well. So welcome to all you guys too. And we'll jump right in. All right, so to cover what we're going to be talking about today, so first we'll talk a little bit about history of LexisNexis, the Nexis Diligence project itself, talk about the use case of the application, about our content pipeline, right? So how are we getting content into our cluster? Some details on the Elastic cluster itself. And then I handpicked 5 challenges. So of course, there's always a lot more than 5 challenges when you do a project, but I handpicked 5 of them that I thought would be interesting for this chat. And then a little bit about future direction, what we're working on now, some things coming up. So I wouldn't normally go back to 1967 to tell folks about LexisNexis, but since we're a group of search enthusiasts and LexisNexis has a long search history, it's a search-based company, so I thought it would be good to go back and give a bit more about LexisNexis. So 1967, a group, OSBA, which stands for Ohio State Bar Association, they signed a contract with Data Corporation to build a full-text, interactive, computer-assisted research service for Ohio statutes. Right, so this is a search. They're looking for a product to do search in 1967, right? Here we are in 2020 thinking we're doing some pretty awesome stuff. I mean, I can't imagine what these guys were thinking in 67 when they're looking for this type of features. So between 67 and 73, a company called Mead Corporation, yes, that's the Mead Corporation we probably all know, notebooks and trapper keepers, of course, buys Data Corporation mainly for their printing technology, and they create a subsidiary out of it called Mead Data Central. And in 1973, that subsidiary launches a service called Lexis, Law Information Service. So Lex is Latin for law, and IS for information service. So that's how they came up with the name Lexis. And of course, I'm getting a call on my very ancient landline, probably was installed in 1973. Sorry about that. So that original Lexis service provided full text of the Ohio, New York, and US codes and case law materials. Between 1973 and 79, Mead Data Central creates its own private telecommunications network, so customers in large cities and university law libraries can have the Lexis service installed right in their offices. And then in 79, they kind of expand upon this idea of attorneys having access to Lexis right on their desktops. So they create the UBIC terminal. It's a little red terminal working over the TIMNet. So this was before the internet, of course, before Al Gore. So it operated at 1200 baud, and it put Lexis right on attorneys' desks. In 1980, they launched a service called Nexis. So whereas Lexis searches over law information, Nexis searches over news articles. And also in 1980, they built a data center here down the road from myself, which is still there now. And then 1984, I handpicked, of course, there's a lot more to this history, right, that I'm not going into, but a couple features in 84 and 93 that I thought were pretty neat, given the date that they were implemented. Eclipse in 84 would present a list of new documents that matched a user search when they logged into Lexis, right? So, of course, we do that through percolation type of features that I'll talk about later on. But in 84, this concept of saving a search and having, showing the new documents that match the search, I thought was pretty amazing. And then in 93, a service called Freestyle, think of natural language processing today, right? So plain English search feature to be used without Boolean logic. In 1994, Reed Elsevier acquires Me Data Central, changes the name of the company to LexisNexis, and of course that stands still now. 2020, LexisNexis completes a migration from 40-year-old mainframe technology. So 40 years obviously takes us back to 1980. So between 80 and really all the way up to 2020, they were enhancing this mainframe, the search features that were built on top of the mainframe. I think the first application that was migrated from that mainframe was done in 2010, 2011 timeframe. And the app that we're talking about today, NEXIS Diligence, was just completed about 6 months ago. We got all the users migrated off. We started the project in early of 2018. And another important date, 1996, I skipped past that one. That's when myself, for the first time, used Yahoo, and my mind was blown. So thinking about sitting there in 96 and being so impressed with Yahoo, again, I couldn't imagine back in 1979 having one of these UBIC terminals sitting on my desk as a lawyer and all the power that it gave me at that in 1979. So the Nexis Diligence product itself. So what does Nexis Diligence do? Well, I'll read the kind of a tagline here, and then I'll explain what it really does. So it conducts thorough person and company background checks to meet due diligence best practices for regulatory compliance. So it's really a tool for searching, reporting, and alerting. So think of a cell phone company, and a cell phone company wanting to conduct business with a third party to make screens for their cell phones. So I'm going to want to look at different screen makers that I may want to make screens for my phones. So I can come into this product. I can conduct a search for these particular companies. That search, when I click the search button, it's going to search across a bunch of different data sets. So I'm going to want to look at different company profiles. I'm going to want to look at, are there any legal cases that exist that this company was a part of, credit reports for the company, news, negative news especially, right? Any bad press for the company. I'm probably going to do this for each one of those companies that I'm looking at to make my screens for me. I'm going to create a report from the documents that I'm interested in that I found during my search. And then it may be several months till I actually close business with a particular company, right? A lot of other hoops and hurdles to go through. So I'm going to want to know also about new documents that are coming in, right? Is there a new credit report? Maybe a company's credit report was very clean. A month later, not so clean, right? I'm going to want to know about that. Was there some bad press about that company? I'm going to want to know that. So that's where the alerting feature comes in. So the content pipeline, how do we get content into our cluster? So I know everybody loves those architecture diagrams with arrows going all over the place, and you got to turn your head sideways to read names, and then when you squint hard enough to read the name, it's some internal name that doesn't mean anything to you anyhow. If you're into that type of thing, sorry, I simplified this quite a bit. So the top components here are things that my team is not involved in, right? We don't build these. We build everything in the light blue boxes down below here. So the first step is content goes through the fabrication pipeline. Again, I've simplified this quite a bit, right? The fabrication pipeline is actually many different pipelines. So we pull content from thousands of different sources, comes in all kinds of different formats, right? We might pull things from FTP, from a REST API, PDF sent to us on disks. If you go back in time, I don't actually know if we do this anymore, but we used to actually have people retyping in printed books and documents. So all kinds of different ways that content is coming in, different formats. So the fabrication pipeline is going to convert all that different content into XML documents, a set of about 50 different schemas. And it's going to store all those documents into the data lake. And then our pipeline then runs on top of that storage. So the data lake manager is first going to pull documents out. So it's responsible for all the different subscriptions to content that we have. So we have about 16,000 different subscriptions to the lake that we have. It pulls out documents. It knows whether it's a new document, whether it's an update to a document, a delete of a document. So we have to be concerned about additions, updates, and deletes. And what it's going to do is it's going to pump each one of those individual XML documents onto a Kafka topic. So between each one of these processes, you can kind of envision Kafka topics being used as the mechanism of getting documents from one process to another. Also, each one of these processes is a Docker. It's a Docker container. So we have the ability to scale up and down as we see fit, right? Depending on the load that's coming in. If we need more transformer power, we can scale up the number of pods on our transformer. And as we don't need it anymore, we can scale it down. So don't think of each one as just a single, individual process. It's scale. It can scale. So getting onto what the transformer does, the transformer is responsible for looking at each one of those XML documents. It's going to know things about what we want to search on in those documents. And it basically has a bunch of XPath configuration, and it's going to go in and start extracting data from those documents and creating a JSON document out of that we're going to later index. So we're pulling all the searchable data out of it. Then it goes on to our duplicates process. So this is done for news articles specifically. So as news articles flow through our duplicate detection process, if it detects highly similar articles, so they don't have to be exact duplicates, it's going to assign a common ID to each one of those documents that's considered similar to each other. And we call that the duplicate group ID. So it's not the main ID of the document itself, it's a separate field. Then those documents move on to enrichment. So we do entity extraction and sentiment analysis. And that is sentiment analysis on the document as a whole and also on each entity that was extracted. So I can know how positive or negative a particular person or company was talked about within a particular document or article. And then that information gets added on in JSON format to the document, and it gets passed on to our indexer and alerts processes. So the indexer is responsible, obviously, for indexing the documents into the cluster. And the alerts process is responsible for also sending those documents to the cluster, but it's sending those to a different set of indexes. It sends them to the percolation indexes. And we'll talk a bit more later about percolation and how that functionality works. So some details on our cluster. So we have 3.7 billion documents total across all those different content types we looked at earlier. That's spread across 32 different indexes. So we have a separate index for each one of those content types, also a separate index for each specific news language that we have. So about 20 different news languages we support, and then the rest are different content types. So from an index perspective, not every index is created the same way, right? So each one is going to have a different number of shards. Those number of shards is going to be calculated based off the number of docs in the index, the disk space that the index takes up, and the query complexity that is run on that index. So depending really on those three separate things, we can determine a optimal number for our shards. And those shards, the shard number does vary. As we get more docs, we'll change the number of shards. If the query complexity varies greatly for some reason, if we've increased it, we may up the number of shards as well. We also use filtered aliases across our indexes. We use a lot of different aliases, but filtered aliases may be a little more interesting. So if a user, for instance, wanted to search across only major US publications instead of all English news, right? They're not concerned about smaller publications, only the major publications. We have an alias, a filtered alias created for that. So it would be created on our English news index and filtered down to the set of sources that we consider to be part of the major US publications type. We have about 290,000 alerts. Again, similar to documents, they're spread across 32 indexes. So really a separate, kind of a one-to-one mapping for an alert index to a document index. This is what we use for the percolation. Again, I'll get into more on that in a bit. The cluster is composed of 82 data nodes spread across 2 racks, so we're not cloud-based. The pipeline that we talked about earlier, pipeline is in the cloud. The application is cloud-based. It's just the search cluster itself is not cloud-based. Lots of different the decision points went into that. I'm not getting into that in this conversation. That would be a whole nother hour-long talk. So the nodes that it's running on, we do run 1 node per server. That's the configuration. Each server is 32 virtual CPUs, 128 gig of RAM. We use 31 gigs for the JVM. So they're pretty beefy machines. We also have shard allocation awareness configured, so we'll never get all copies of a particular shard onto a single rack, right? So shard allocation configured across the 2 racks. We have 4 separate coordinating nodes. So we have 2 nodes specifically for ingestion, 2 nodes specifically for searching. So from a coordinating node perspective, we didn't want the ingestion process to slow down our searching. So that's the reason for the kind of the 2 and 2 split, all indexing go into 2 of them, all searches going to the other 2 coordinating nodes. And of course we have 3 master eligible nodes as well, and 1 Kibana node also hooked up to the cluster. Okay, so moving on to the 5 challenges that I mentioned. So challenge number 1, supporting legacy syntax. So of course we're migrating this application from older technology, and especially the search part of it that was running on a mainframe system with those 40 years of enhancements on top of it. So of course they had a lot of different things we had to support from that aspect. But what this is talking about specifically is custom proximity connectors and the at least operator. So proximity connectors, these are within and preceding connectors. So you can read this as within n, within paragraph, within sentence, preceding n, where n is any number. So for example, George within 2 of Ruth. If I'm looking for perhaps George Herman Babe Ruth or Ruth comma George, I could do George within 2 of Ruth and it would match both of those, right? It would look for any occurrences of the term George within 2 terms of the term Ruth. It also works as it works on the phrase level, so Babe Ruth within 10 of New York Yankees. So again, any 10 terms could be in between the phrase Babe Ruth and the phrase New York Yankees. It also deals with proximity logic, so you can do George or Babe preceding 2 of Ruth. So preceding will enforce that the term George or Babe has to come prior to Ruth. If it was Ruth comma George, it would not match that. And the at least operator, so at least n, an example, at least 5 of a home run. So it's not, it's not good enough if Babe Ruth hit 1 home run, but if an article mentions home run 5 times, then we want to match that. If it's only mentioned 1 time, not good enough for me. At least 2, George within 2 of Ruth, right? So just showing that all these different connectors and operators can be nested. The syntax that I'm putting in here is rather simple compared to the way users are actually crafting their queries. So dealing with a pretty high degree of complexity with the nested proximity connectors. So how did we solve this challenge? How did we implement these custom connectors? So search API magic. So of course we have a custom search API that sits between our cluster and the application. So any search that the application does, it always calls our search API, and then we turn around and call the cluster. So we chose that architecture for many different reasons. So within that search API, we put in some parsing logic, right? So every query that's coming in, we're parsing, looking for these connectors and operators, and then we're generating span queries from this. So it's very common for us to actually generate several thousand lines of span query syntax. And then when you're trying to debug issues in there, it's really fun because you actually have to read through like every single line sometimes to find an issue. But we're generating the span queries. So for example, George within 2 of Ruth, that would generate a span near query with 2 span terms. It would have a slop of 2 for the within 2. And in order set as false for within. We would set the within order or the in order to true if it's a preceding connector, right, to enforce that the term before the preceding connector has to come before the term after it. So that in and of itself is kind of fun, but we also had to do pre-analysis on the terms, right? Because span queries operate only on the term level. So if I were to put in George with a capital G or Ruth with a capital R, I have the lowercase filter applied to my ingestion pipeline, and what would happen is I would get no matches. So we have to perform the same analysis on these terms before they're put into the span queries as the analysis that's performed during ingestion time. So we basically call out to the analyze endpoint with the terms that we're going to put into the span query to get back the analyzed terms, and that's what we use in the span query syntax. So challenge number 2, supporting BOOLEAN users. So we actually have a whole different classification of our different types of users and the way they search, anywhere from novice to novice, expert, novice, expert. I'm not going to get into what all those different things mean, but this particular set of users that I'm talking about here is that set of users that like to carefully craft the exact query they want to be run, right? So of course we have things like stemming and index terms, German decompounding, these type of filters going on. But for this particular set of users, they don't want any of that magic to happen. They don't want the magic of stemming. They want to be very specific about what they want to run. So part of being very specific is that they like to use wildcard characters. I know that seems a little weird, specific and wildcards at the same time. but that's how these folks like to operate. So when we're looking for negative news strings, right? So part of the search is looking for negative news about a company or person. So we have the ability to craft negative news strings within the application. These are saved off, so you don't have to put these in every single search. So arrest, wildcard, bribe, wildcard, kidnap, wildcard. Again, this is very, very simple compared to the negative news strings we actually see. They're typically somewhere between 50 and 100 different terms and phrases. Usually about half of them are using wildcard characters. And then it gets real fun for German, because the German users don't just have trailing wildcards, they have leading wildcards as well. And of course, individual terms with leading and trailing wildcards on the same term. So I'll talk a bit more about this second example in a bit. So taking a look at just this first example, if we did nothing at all and we're forming span queries out of this, right? If I have within connectors or whatever, and we also actually do proximity of the entity, so proximity of the person or company that a user is searching on in proximity to the negative news string itself, right? So I want to find Babe Ruth. Of course, Babe Ruth would never do anything bad. I don't know why I'd look for negative news on Babe Ruth, but if I'm searching for Babe Ruth, I'd want to find Babe Ruth within 25 words of bribery. If it talks about Babe Ruth at the beginning of the document and bribery at the very end, it's probably not talking about Babe Ruth accepting bribes or something of that nature, right? So that's where the proximity comes into play. So we're forming a lot of span queries from that aspect too. So if I do nothing at all, I have the Boolean max clause count in Elastic that defaults to 1024. And what basically happens is if I'm using a span prefix clause for each one of these wildcarded terms, it can expand to a max of 1024 different terms. So right away, what obviously happens is I have potential for long-running queries, right? Queries can take a long time to run, cause memory issues, and so on. So you could sort of solve this by using the top terms n feature, where n, I could define 1024, and that's going to pull out the top 1024 terms that bribe wildcard would expand to. But those top terms aren't top terms by frequency or by inverse document frequency. It's top terms alphabetical, right? So some of our terms we were seeing would actually expand to 100,000 plus terms. It's pulling out 1024 alphabetically. If it's bribe asterisk, this isn't a real good example, but it wouldn't even get to like bribe B, right? It was only in bribe A. So we weren't matching on all the terms that we should be matching on. So long-running queries not really performing the query correctly. So how did we solve this? So I probably should have like hidden the right side of these so you weren't cheating and jumping ahead. But how did we solve this? So we use index prefixes. So index prefix is very, very simple to implement. So pretend this is a mapping in our index, and I have a field called content. It's of type text. I have an ingest analyzer, a search analyzer. Now I just simply configure index prefixes. In our case, we give a min number of characters as 3 and a max number of characters of 19. What this does behind the scenes is it's going to create a field called content._index_prefix. And within that field, let's say I'm ingesting a document and it has the word number in it, so number. I have my min chars of 3, and it works very similar to Edge Ngram. So it's going to index num, it's going to index numb, numbe, and number. So now when I'm doing a span prefix query, or even a query string query will work as well when I have a wild card at the end of a term. Elastic automatically knows magically that, hey, you're doing a prefix query. I have index prefixes applied to the field you're searching on. It's going to automatically look in that index prefix field that I've created by using this configuration, and it's going to match on that. So now instead of having to expand to 1,024 terms and missing terms, it's going to match on a single term. right? Because I have all the different prefixes indexed. So I'm no longer missing documents, no longer running queries, works very fast. So why do I have index prefixes / ngrams? So I mentioned we come back to the second example, the German example. So index prefixes isn't going to work for this particular case because I have a leading and a trailing wildcard that I want to match on. And this is common in German because they have very long compound words. It's very common to have 10 different words compounded together and you get this huge long word. And I mentioned, yes, we do German decompounding, but users like the ability to do this kind of behavior as well. So we in a more manual fashion create a field similar to index prefixes. We could call it content.ngram, and we would apply the ngram filter on that, and very much in the same way that edge ngrams and index prefixes work. I'll now create my ngrams and match on individual terms in that content.ngram field. The challenge is that I have to know which terms to do that for. I wouldn't want to do that for a term that doesn't have leading and trailing wildcards because you would match on a whole lot more stuff. So we have some fairly complex logic to figure out which field to search against and get the whole query mashed together properly so we get a good hits coming back. So challenge number 3, deduping news articles. So what's very common in news is that different publications will publish very similar articles, right? Almost exactly the same thing. So what we didn't want to have happen is a user does a search and their top 20 hits in their list are basically the exact same article coming back just from different publishers. So what we want to do is we want to collapse those articles so you get a single hit in your list, and then you have a little plus sign that you can click on to expand and see when you expand it, we show the top 5, and then you can click more and keep clicking more to eventually see all of them if you wish to. So how did we do this? Well, it started back in the duplicate detection process that I talked about in our content pipeline. And in there, we use locality sensitive hashing. Won't get into exactly what that does, but we use the min hash algorithm, and it's a way of detecting similar documents. And the final goal of that duplicate detection process, like I mentioned, is that we have a duplicate group ID stamped onto every individual document. And if I were to do a query for one duplicate group ID, if I get back 10 documents for that, that means that those 10 documents are similar to each other. So since I have similarity kind of through that duplicate group ID, I can apply field collapsing. So field collapsing gets done on the query. It's pretty straightforward to add onto your query, a little bit of syntax, and as a result, you get exactly what I just shared, is that you end up getting 1 hit instead of the 20 hits, and you can actually get back inner hits as part of that field collapsing query as well. What we chose to do is to not get the inner hits back as part of that main query. We were actually seeing that it limited our throughput quite a bit to do that, because behind the scenes, what Elastic actually does is, let's say you have 50 different hits come back on your first page. It's going to actually spin up a search thread for each one of those 50 hits, looking for the similar docs or the inner hits in this particular case. So we didn't like all the extra search threads being spun up across our cluster. So what we're doing is we're applying the field collapsing, we're getting back the single page of hits, and then we make a second query, one query, that we pass in all the duplicate group IDs for that 50 documents on that page, and it's going to pull back the number of documents that corresponds to each duplicate group ID for us. So instead of spinning up 50 new searches across the cluster, albeit very fast running searches, we're sending out one query instead, and then when the user expands by clicking on the plus sign, they want to see similar documents, then we initiate separate queries for that as well. But those are only initiated at the point that the user is saying, hey, I want this action. I'm clicking the plus sign. I want to see more, right? Most users will never click that plus sign. So there's no point in doing all of the extra processing to bring those documents back as part of the first search. So challenge number 4, search expanded abbreviations. So we call these things abbreviations, equivalents, and synonyms. So I thought it was, appropriate to use all 3 of those terms on my slide as well, since it's we use them as equivalents to each other in our everyday speak. So company equivalents. So I have a couple examples here. So if I'm searching for Apple Inc., the intent is that I want to match Apple Incorporated, or vice versa, right? If I search for Apple Incorporated, I also want to match text that contains Apple Inc. If I were to search for Apple LLP, I want to match Apple Limited Liability Partnership, and vice versa. If I'm searching for Apple Limited Liability Partnership, I want to automatically match Apple LLP as well. So this can be solved with the synonym filter. So the first step of this is to create a synonyms configuration file. And it kind of looks like exactly what I have here. So how this works is this would be on a single line. It's split across two separate lines on the slide here, but on a single line, I would have Inc, Incorp, Incorporated, and then the same thing on the right side of the equal sign. So if I have my synonyms filter applied on the ingestion side, if a document comes in with Inc, it's going to automatically index Inc, Incorp, and Incorporated also. Similarly, if it comes in with Incorporated, it will automatically index Inc, Incorporated, and Incorporated. Same thing with LLP, Unlimited Liability Partnership. So there's actually two options for configuring this. So you can add the synonym filter to the ingestion analyzer. And that's kind of the example that I just talked through, right? On the ingestion side, if it matches one thing on the left side, it will automatically index the terms on the right side as well. But you can also add the synonym graph filter to the search analyzer. So you can do it at ingestion time or at search time. The advantage to the synonym graph filter over the synonym filter is that it accounts for multi-term synonyms. So the example of Apple LLP and Apple Limited Liability Partnership, it's able to account for these multi-term synonyms better than the synonym filter analyzer. And if anybody is interested in more detail or what we've done there, you can reach out to me. I'm not going to go into the nitty-gritty detail between these two filters. I would say if you're looking for this kind of behavior, I would definitely read through the details on both of these and test both of them out. In our particular implementation, we're actually using kind of a hybrid between the two. So we have a field created without the synonym filter applied and one created with the synonym filter. And in certain situations, we'll search the field with the synonym filter. And in certain situations, we actually search using the synonym graph analyzer against the field without the synonym filter applied on. And there's reasons for doing that, which would probably be another hour-long talk. So challenge number 5, alerting on new documents. So we want email notifications sent out for as documents come in that matched a saved query is the gist of it, right? And we want users to be able to configure the frequency that they want these email notifications sent to them. So do they want to be sent hourly, daily, weekly? They can, if it's hourly, they can, or not hourly. If it's hourly, it's going to be hourly. If it's daily, they can configure the time of day that they want them to be sent. So what we've seen in other products is it's very common for users to configure daily at 8 a.m. Well, if 75% of your users are configuring, I want my emails at daily at 8 a.m., what we were doing in those other products is we take all the saved searches and we run those at 8 a.m. Of course, they can't all be run at the same time, right? We would kill the search system if we run them all at the same time. So what we were seeing was some users would actually only get their email notification maybe an hour later, right? It could be 9 a.m. instead of 8 a.m. that they're getting their their email notification. So we did not want that delay in email delivery. So what we did to solve this is percolation. So with percolation, it's kind of the reverse of normal document matching. So instead of storing documents in an index, you actually store queries in your index. And then as documents come through your ingestion pipeline, you're indexing those documents obviously into your document indexes. In addition to storing those into your document indexes, you're sending those to your percolation indexes. And what that will do is it will respond back with the queries that match that document, right? So if that document were to be in your index, which queries would pull that document back? It is actually rather easy to configure. So when you're setting up your index mappings, if you just add this little bit of syntax here, query type percolator, that's where your queries are going to be stored at. And then the rest of your mappings are going to mimic your document mappings. So you still need all those mappings because behind the scenes it basically stores a set of documents in your index, and then there's some magic to figure out which queries it runs or which queries it would match. But at the end of the day, there's some more complex queries that it can't do that magic with, and then those complex queries need to be kind of automatically run against the documents that it's storing in the index. Now that was kind of a probably overly complicated explanation of that. But the idea is very simple to implement, just add query type percolator. And it will respond, again, the response comes back with the queries that the document matches. And then you can take this response, and then we have logic on the response side of that to look at every response coming in, and we basically map the list of documents to each saved search. So first, say I have one saved search. As documents are coming in, I'm queuing up the IDs of those documents to be sent out. So actually it does more than IDs. It's queuing up all the information that's sent in the email. So now at 8 a.m., instead of running all those different individual searches to pull back the number of documents, I have a list of the exact documents that already matched since the last time that, since the previous morning at 8 a.m. So now I can just format my email and send it. I don't have to do any of the search logic. So makes that sending process much, much, much quicker. Of course, whenever you're making something quicker, you're always making something slower, right? There's always a trade-off, right? There's always, I'm doing something at indexing time to save on search time, or I'm doing something extra at search time to save on indexing processing time. So in this particular case, my email notifications are faster, but I'm adding a lot of overhead for the percolation, right? So I have a lot of these percolation indexes. From a disk space size perspective, they're small, right? They hardly take up any space. But from a CPU perspective, there's now a lot of extra processing going on, right? There's a lot of extra searches going on while documents are being indexed. But in our particular situation, our cluster is large enough to handle this. We sized it appropriately to handle this percolation logic, and it fits us pretty well. So now some things that were, I'd say, in the very beginning stages. Some of these are things we're just kind of thinking about. Some we've started some proof of concepts on. So using interval queries instead of span queries. So I mentioned the thousands of lines of span queries that we're forming for certain queries. So we want to go away from span queries and use interval queries. We've done small proof of concepts for this, and we think it will work quite well. We need to test it out a bit more, but the goal is that we'll have a little less verbose syntax, we're hoping, which is nice by itself, but not the main goal of it. Analysis is performed with interval queries. So whereas span queries operate on that individual, on the term level, with interval queries, the analysis can actually be applied. So that pre-analysis step that I was talking about with the within and preceding connectors, the hope is that we would no longer have to do that pre-analysis step, that it will be done when we run the query. and kind of some of the oddities we have with our synonym and synonym graph filters in our hybrid approach. We're hoping that we can go completely away from the synonym filter on the ingestion side and use synonym graph filter only on the query side. So I phrased this, perhaps we can switch, and that is because that's part of the testing that we actually haven't done with the interval queries yet, extensive testing on that. We're wanting to implement the annotated text plugin. So of course we're doing entity extraction. Part of our entity extraction is we get back normalized names. So normalized names are if I'm looking for, if a document contains Bill Gates, the normalized name might be William Gates. It continues to talk about Bill, normalized name is still William Gates. It continues to talk about Mr. Gates, the normalized name is William Gates, right? And we have IDs for each one of these normalized names as well, and positional information for where it was found in the document. So we're not doing a good job of using all this different information at this point in time, but with the annotated text plugin, what we can do is we can inject that information into the point that the entity was mentioned in a document. So if it talks about Mr. Gates at a certain point of the document, we can actually inject that is William Gates. We can inject an ID for that name. And now we can search, instead of doing full text search across our documents, we can search across entity information, and we can run proximity queries on those entities instead of proximity on individual terms of text. So if you're interested in that sort of thing, definitely recommend looking at the annotated text plugin. Again, we have not implemented it yet, but we've done some tests with it, and it works quite nicely. We're pretty darn excited about it, actually. And then the third item, implementing Elastic Graph. So this is something that we probably took a look at for the first time maybe even 2.5 years ago at this point. And a lot of our product management group was very excited about this. It gives you a completely different mechanism to explore your document set. Right, so I can see Bill Gates. I can see his relationship to Microsoft between, the number of times that Bill Gates and Microsoft was mentioned in the same document, and I can kind of navigate this graph structure, and I think it would be very first very fun, but a very nice feature for our users too, to explore the data in this additional fashion. So I'm hoping we're going to get some time to do some more testing with that, some more proof of concepts, and move that forward. So with that, I want to say thank you to everybody for joining and listening to me babble for a while. And if you liked my slides by chance, I don't take credit for the template. I got it from SlidesGo. If you didn't like my slides, well, they would have been absolutely awful without this template. So thank them as well, even if you didn't like them. And you're definitely free to reach out at me at my email address or LinkedIn, and can open it up to questions. I don't know if any have come in during the presentation or not yet.
I haven't seen any yet,
okay.
But perhaps that's because you just did such a thorough job walking us through the implementation. Thank you so much for coming on today, Clint. It's really awesome to get to see and hear from y'all.
Sure. Yep. Happy to be presenting. I enjoy talking about this stuff. So I live and breathe it every day. So it's fun for me.
Awesome. Yeah, we do have a question. Matt asks, what is your typical node size?
Typical node size. Yeah. So we do configure one node per server, and each one of those servers is 32 virtual CPUs. It has 128 gigs of RAM. We configure the JVM for 31 gig. we probably, from a number of index perspective on the node, probably, or not number of indexes, but number of shards. There will probably be 16 to 17 different shards living on each node. That would be a combination of different percolation indexes combined with document indexes. Hopefully that answered the question.
We have another question, a follow-up question. What indicators are you using to scale up or add nodes?
Yep, that's a good question. So first, how did we size the cluster to start with? So we actually took a representative document set and indexed it, and we attempted to come up with representative queries that users would actually run. And of course, we're migrating from an old platform to a new platform, right? So we had the luxury of kind of knowing what our document set was, knowing what type of queries are going to be run against it, knowing the throughput that we're expected to see, right? So we tried to mimic this environment at a smaller scale. Right, so we started by having a single node with one index with a single shard, loading that shard up to its breaking point, right, and running queries against it. And at the point that we thought we hit its breaking point, then we would add multiple shards onto the node to the point that we hit its breaking point. And we would do rounds and rounds and rounds of these rounds and rounds of these tests, probably a couple months of worth of testing to try to scale this cluster, again, because we weren't going cloud-based. So we were really trying to, I guess, get our cluster size right. Now, of course, it's not the end of the world. We can order more hardware and so on and so on. But we got it pretty right, actually. So that 82 data nodes is actually the original cluster size. We do actually have another 41 servers of hardware, so a third rack that's sitting in the data center right now, ready to be put in. That's really there for additional projects that we're looking to move over to the same cluster. So at this point, we haven't had to scale our cluster up just for the individual application that's running on top of it now. But we do pay very, very close attention to stats, to CPU, disk space. And as I say that, I'm recalling some additional information. We have had to, we actually upped the number of CPUs. So the original servers were 16 virtual CPU. There was another socket on each one of those, so we did end up putting in an additional CPU in each one of those sockets, which was an additional 16 virtual CPUs. And we did that primarily because we saw the percolation, and we said, okay, if we get this many more alerts configured and so on, we better go ahead and put those CPUs in now. Looking back, I think we would have been okay at this point, but I'm happy they're there.
Awesome. There's another question.
Yep.
How large are your individual documents and or shards?
Yeah, so individual documents, documents can vary greatly, just because we have some documents that might be 100 words in length, and I'm using words as a way to quantify the size of the documents at this point, but they might be 100 words. They might be thousands and thousands of words, right? We have full cases in here, right? So when you're talking about case law material, court cases can be quite large. So that's where, you know, for our index that has cases in it, the number of documents per shard is going to be a lot less than another index that has smaller documents in it. So from a disk space perspective, the general rule of thumb I typically hear is try to keep your shards under 40 gig, and that varies a little bit from 40 to 50 gig or so, but that's the general rule of thumb. I'll say we're well above that point. We actually hit 300 gig on some of our shards not too long back. And of course, that was in an index where we started ingesting additional sources. And at the beginning of that, we honestly had no idea how much content these new sources were going to give us. So our shard size got too large. We consider 300 gigs definitely too large. So we increased the number of shards. So right now I'd say every shard we have now is under 100 gig. We would like it to be smaller from a disk size perspective. Sure, it's easier to balance them out and so on, easier in a lot of different ways. But we really use query complexity and performance as one of our measurements, and if we're able to cram more documents in, we tend to lean towards that avenue because we really want to limit the number of search threads we're spinning up across the whole cluster. So it's always a balance. But the short answer is under 100 gig for shard size.
Awesome. Well, thank you so much, Clint. I think that's all the questions that we had today. Really appreciate you taking the time to come on and talk through all of this with us.
All right, awesome.